Hi guys, so today we will be discussing the two harder problems of division 1. We will not be going over the last problem. Like I can maybe give a brief overview of it at the end of the session, but like the last problem, jumping fever, requires a separate video on its own probably because it's quite complicated, right? So we will be discussing Xor Jar Muluk Tar and DOTTIME. Both of these problems were around medium difficulty, 60 submissions, 50 submissions. Okay, so let's get into it. So first is this Xor Jar Muluk Tar problem. Here you are given array, or rather a sequence or whatever, A1 to AN, and then you are also given some relations L to R, rather some pairs L1, R1, L2, R2 as given in the problem, right? Um, and then, so first you have the initial array, right? A1, A2, dot AN. Now from there you create an array B1, B2, B3, up to Bn, right? How, what is the relation there? So see, we for bi we XOR the values of a li plus 1, a li plus 2, right, up till a r1, or rather a ri. So I mean, here it's given in a different note, in a bit of a different notation. Here it says that a to the power k, a to the superscript k, is effectively the state of the array in the kth round, and the array B that I was talking about, it is effectively a to the power k plus 1, or here it's a to the power k. The previous round was a to the power k minus 1, and so from the previous array I XORed all the elements from li to ri, right? Li, ri are what? It's given in the input. L1, R1, L2, R2, all these pairs are given in the input, and then I create the new array, right? So in this way, in each iteration, we can create the new array from our previous array, and what we want to answer finally is this a to the power k, right? So doing this iteration k times. Um, for the constraints, it's n is 500, k is very large, so k is actually 5 into 10 to the power 7, right? And ai is 10 to the power 18. So how do we go about this problem, right? So notice that the subtasks aren't really much of a help here. I mean, okay, sure, you have n is less than 100, here it's 500, but uh, like whatever your complexity will be, 500 and 100 won't make that much of a difference, right? Similarly, test cases are 1 and 3. So the basic approach of the problem is probably similar for both the subtasks. It's just in the first subtask, the constant factor is maybe a bit lower. In the second, uh, there's less of a leeway as to what you can do, right? So I don't think we can glean too much information from the constraints just as of yet, right? Because n is 500 means it can be an n square problem, it can be an n square log n problem, it can be an n cube problem. So okay, so let's try to see what this thing actually means, right? Okay. So first thing that we see is that we are taking a XOR, right? And XOR, you can, whenever you see XOR, or rather any bitwise computation, it's always a good idea to think, okay, what if we separate each of the bits and then compute something for each of the bits differently, and then just club them together at the end, right? So that means that instead of dealing with any number in our array, so here the array numbers could have varied from 1 to 10 to the power 18, right? We just have zeros and ones now. Okay, so that's and see, the ith, let's say the ith bit and the jth bit of a number, after how many operations we do, XOR does not affect the, like, XORing something at the ith bit does not affect anything at the jth bit, like, so you can effectively just break them up into each bit and do the computation. I hope that makes sense why it does not lead to incorrect results. Uh, okay, so let's take a, so now what we have reduced our problem into, we only have zeros and ones, and we still want to do this operation, right? We still want to do this XOR operation. Another interesting thing in XOR is adding two numbers a plus b, like a XOR b. If you are considering a and b just to be 0 and 1, it's effectively a plus, like if a and b are 0 and 1, then a XOR b is effectively a plus b mod 2, right? So this is another well-known fact. um, Let me just 0 1. So basically if you do 0 XOR 1, so XOR's symbol is this one, right? um, yeah, so 0 XOR 1 is 1, 1 XOR 0 is effectively the same, 1 XOR 1 is 0, right? So 1 plus 1 mod 2 is again 0. So effectively XOR is basically addition plus the modulo 2, right? So what do we effectively have to do? So initially, let's say our array was 0 1 1 0 1, and then we are given some L1 comma R1 indices, right? So let's take an example, L1 R1. Let's make this a 3 is just 3 elements array, just to give a simpler example, right? L1 R1 is, let's say, here 1 comma 2. um, L2 R2 is, let's say, 1 comma 3, and L3 R3 is just, let's say, 3 comma 3. Okay, now here this XOR symbol is now a plus symbol, right? So let me write it down as well. A let's call the initial array B, and after we, let's call the initial array A, and after we do the transformation, let's call the next array that we get B. So A here is effectively a to the power k minus 1 in the problems notation, and B is just a to the power k, right? I'm just using the terms B and A here. So B is just, we are now doing addition, right? We are not doing XOR. So B is just A1 plus A2, right? This is B1, right? This is because in our L1 R1 condition, we had 1 comma 2. Similarly, B2 is equal to, what did we have? Yeah, A1 plus A2 plus A3, right? And B3 is equal to A3 only, I guess. Yes, it's just take. Another that we can represent it. So this comes in the some a linear. You have either a 0 or a 1 as the coefficients for each AI, and then you just add a linear combinations of those AI, right? And this is a very specific linear combination here. So I'll just reiterate the last 2 minutes or so, because just if anyone could not hear. So what I said was, here, as I had written this BI in terms of AI, right, according to these L1 R1 L2 R2 L3 R3 rules. Sorry. So yeah, so as we are creating this BIs from the previous array, we are effectively taking a linear combination of some of the elements, right? So here I am taking A1, A2, and no A3. And what's more, this is like a special kind of a linear combination, in the sense that you either take the element or you do not take the element, right? The coefficients are either 0 or 1. So how do you visualize this in terms of a linear recurrence? Like, rather to expand this as a linear recurrence of zeros and ones, you can do something like A3. And then here also for the second element, for calculating B2, we also have, you can write it as this, right? And for B3, you can write it as, right. So yeah, so we are just taking a linear combination of the previous values of AI, and then forming the new value of like bi, right? So from linear combinations, it should like, what's the standard way or what's the most common way of solving linear combination, rather problems with linear combination? Matrix exponentiations, right? So here you can even see how this can, like, this takes the form of a matrix, right? Because let's say a was a vector, correct? And then you are effectively multiplying it with a matrix of this sort and then getting a new vector b, right? So that is how we generally treat linear combinations, correct? So what is the matrix for this example? The matrix M. So we are effectively doing B is equal to A star M, right? Now what is M here? So A is just like, I'm denoting it as A1, A2, A3. We had taken a specific example, but that does not really matter here. M is, so for A, M is basically something like 1, and then below 1 we will have another 1, and then, okay, I think I can insert a table here. It's easier. Yeah. So this table is effectively our matrix, let's say. So we will have a 1 here, a 1 here, and what did we multiply A3 with? 0, right? So 0. Here also we will have 1, 1, 1, and here we will have 0, 0, 1. Oops, not here. So this table is effectively our matrix, and we are multiplying the vector A. So we are taking each row of the vector A and multiplying it with each column, right? That is, so let's say the first row, when we multiply the vector with the first column, we get A1 into 1 plus A2 into 1 plus A3 into 0. This is exactly what B1 was. Similarly, when we multiply it with the second column, we get A1 into 1, A2 into 1, A3 into 1, right? This is what we had here. And similarly for the third row. So how do we create this matrix? So now our problem is kind of reduced, right? Each operation is effectively just multiplying this matrix with our vector A, and what we get the next vector, right? So if we had A k minus 1, if you remember our notation from the problem, we get A k after one multiplication with the matrix, right? So how many times do we effectively have to multiply the matrix? K times to get the final vector, right? Or k minus 1, I guess. So there's an, okay, so you initially have A. If you multiply it one time, you get A to the power 2. So to get A to the power k, you need to multiply with m to the power k minus 1, correct? Okay, so now how do I construct this matrix in the first place? Well, it's just L1 R1 is for column 1, L2R rows are 1, all other rows are 0, right? For column, for rather, like, now to generalize for column I, Li comma Ri, if the condition is Li comma Ri, that means for all rows between L to R, column I, like the intersection of column I and all rows L to R is 1, and the rest of the column is filled with zeros, correct? So this should come directly when you kind of write it in this expanded form, right? So the matrix construction is easy. The last remaining part, we have to exponentiate the matrix. Now this is a bit tricky, right? Because so usually matrix exponentiation takes what, log k, like n cube log k times, right? So n to the third log k time. Now n is kind of large here. Okay, so n is 500. So n cube is something like 500 cube, right? So that's 10 to the power 6 into that's effectively 10 to the 6 into 5 cube is what, 125. So 10 to the power 2 into, yeah, so something like this. So it's effectively 10 to the power 8, and then again you have the log k factor here, right? So as a rule of thumb, you can usually do about 2 to 3 10 to the power 8 calculations per second, like basic calculations per second. And obviously log k will also vary up to what? Log k is up to 10 to the power 7, so log k can be up to 20. So 2 into 10 to the power 9 calculations, it's definitely not possible in whatever time limit is given. Like it's given 2.5 seconds, but still it's not possible. It is possible to solve the first test case, right? Oh, so you have 3 test cases. Okay, so it is indeed possible to solve the first test case, right? Using this just a simple matrix multiplication using a Boolean array. To solve the second subtask, uh, just doing a just representing the matrix as a Boolean matrix like Boolean 2D array and multiplying is not enough. Wait, did I miss something? Okay, I think I missed something. Just to clarify. Okay, okay, I'll get it. I'll get back to it later. Okay, so remember how we said that everything has to be taken in modulo 2 because Xor is basically addition modulo 2. So just remember that when you're doing this addition, you are just taking a modulo 2 here, right? Okay, let me just decrease the font a bit so that it's visible at least. Yeah. So you are doing a modulo 2 here, okay? Remember this. Now, uh, so what do we have to do? Um, how do we make it fast? Because obviously just representing it as a 2D Boolean array will not be fast enough. What we do is we represent the whole matrix as bit sets. Okay, so bit sets are basically kind of a trick to represent Boolean arrays to get the computation down by a factor of 32 or a factor of 64, depending on um, that I guess depends on the word, like length of word of the processor or something, right? So you can think of it as a division by 32 worst case scenario. Usually it's 64, I guess. So yeah. So now effectively when you use a bit set, right, you effectively get a factor of 64 down here. So now it's computable easily in the time given. So this was the only trick, like only thing that you needed to take care of after getting the observation that, okay, this is actually a matrix multiplication. This trick you needed to take care of to compute um, the matrix fast enough, right? Okay. So, okay. So what else do we need to take care of in this problem? I keep on thinking I'm forgetting something. Okay. So how do you represent this as a, like how do you do the operations using a bit set, right? So if you represent the all the rows and all the columns as bit sets, you are effectively, when you are doing a matrix multiplication, you are taking a row multiplying with a column, right? In our usual algorithm, what we did, we took each element of the row, like the first element of the row, first element of the column, multiplied, second element of row, second element of column, multiplied, right? Even here, how do we speed that up using bit sets, right? So notice that all the elements of the matrix are still 0 or 1, right? Because we are always taking a modulo of 2. So we are doing all computations in a modular field of 2, right? So everything is still 0 and 1, however much you multiply. Now, so what do these elements mean? So if one of the places is 0, right? So if the let's say we are multiplying uh, mij, right? Usually what we do is we take mik into mkj for, and add this up, right? So we take a sum over this, we take a sum over this for all k. This is our standard matrix multiplication thing, right? So notice that if, so mij or any mij can only be 0 and 1. So if mi comma k is 0, or mk comma j is 0, then the result is always 0, right? So let me make a somewhat of a truth table here, okay? So again, let's insert a table. Okay. So this represents m I j. This is k. So okay, so basically the above, like the above row is basically mij and mik, and the first column is mkj, something like that. So what are the possible values? 0, 1, 0, 1, right? Now if both are 0, we get a 0. If 1 is 0, 1 is 1, we again get zeros, right? We are doing this multiplication, right? We again get zeros. And if both of them are 1, we get a 1, correct? There are no other possibilities. Uh, okay, 1 second. Someone is asking, we will discuss about the implementation of segment trees from yesterday's problem. Yeah, we will do it, but after the contest, I guess, like after the discussion of the two problems that we are going to do today. Yeah. Okay. So we have zeros, zeros, ones. So what does this kind of remind us of, right? This is basically the truth table of AND operations, right? Like if you have both zeros or any one of them is a zero, we get a zero. If both of them is one, it's a one, correct? So effectively this multiplication thing is just ANDing the two values, and bit sets can do AND operations very fast, correct? So effectively what we can get is we can compute all of these numbers, like so let's say our bit set C3, it essentially is B3, but we are representing it as a bit set. So let's say A1, or rather, okay, so we are multiplying using a matrix. So bit set C3 will just be, let's say A1, A2, A3 are, we are taking it this example, right? 0, 1, 1. So just to remind you, A is 0, 1, 1. So here it will be just 0, 0, 1, right? And we, so this is the value of B also that we, like, this is not the value of B, but this is effectively each position denotes what is the multiplication value of this place, then this place, and this place. Note that this 0, 0, 1 is not the value of B3, right? Value of B3 would have been whatever indexes, whatever values are there in C3, we just add them up. So we just do 0 plus 0 plus 1. This is the value of B3 that we would have got. If this had been 1, 0, 1, then B3 would have been 1 plus 0 plus 1, right? Now, how do we get the value of B3 from C3? Well, just count the number of ones here. So this is given by the operation, I think, if you have a bit set int B, we can do something like bit b dot count. So I think b dot count gives the number of set bits in the bit set, right? And then we just do B3 is effectively b dot count mod 2, right? Because remember this mod 2, we are doing everything in modulo 2. Everything has to be 0 or 1. That is why this mod 2 is still there, right? So something like this. So effectively, let me give a visual representation just to clarify it. So this is our matrix. We have 4 columns and 4 rows. And I'll just draw another matrix of the same. So the two matrices that I'm drawing are the same matrix. I'm just drawing just to show the multiplication better. So, okay, so how does matrix multiplication work? We take this row, we let's say take this column, and we multiply each of the corresponding elements, right? Now, what we do with matrix multiplication, we immediately add them. We keep a variable sum and then we keep on adding it to sum, right? Instead of that, let's think of it as these two multiplications. Let's say this gives me another sequence, okay, of again n characters. N is 4 here. Okay, so n is 4 here. So we again get 4 values here, like corresponding to each like row element, column element multiplication. And instead of directly just keep on calculating the sum, we like, so if this was 0 0 1 1 and here it was 1 0 1 0, this array that we would have got after corresponding multiplications is effectively 0. Like we multiply 0 with 1, right? Then we multiply 0 with 0, it's again a 0. Then we multiply 1 with 1, it's a 1. Then we multiply it 1 with 0, it's a 0. Correct? So we what we are doing using bit sets, we have this row as a bit set, correct? We have this column as a bit set. This, to generate this array, instead of pairwise multiplication, here pairwise multiplication is just ANDing the corresponding elements, like the bitwise AND. So if you do the bitwise AND of that row and that column, we get the resulting bit set, right? Now you do a sum of this, right? Like basically sum in the sense that you do dot count, that gives you number of set positions, and then you do division, like mod 2, to get whether the value is 0 or 1. So this is how you do the like computation for each of like the matrix multiplication in a much faster way than individually iterating over all the elements and computing the product of 0 and 1 and then doing the sum. You do it as a single bit set operation. That makes it faster by a factor of 32 or 62 or something like that. Yeah. So yeah, so this is how you are effectively reducing the problem to a matrix multiplication thing. Okay. Um, yeah, I guess this was effectively it. Yeah. So I hope the problem is clear. What you did was this is actually just additions in the modulo 2 field. If we consider each bit separately, then it just becomes a modular exponentiation problem. You just figure out the matrix. It's very easy to do using the L1 R1 conditions. You just do a matrix multiplication using bit sets. This was a bit of a tricky part because a lot of people, I think, did not use bit sets initially, then got a TLE, and then you like figured that okay, we need to do it faster. And yeah, so that's about it. Any doubts in this problem in any of the steps, you could write in the chat maybe. Or maybe just press a yes or no on the polling section. Not the polls, I mean there's a yes or no on the managing member part. Okay, so I'll assume that this problem is more or less clear, right? Okay. Now the next problem, dot time. Okay, so dot time is you are doing a dot product. So what's given? You are given an array again, and here you are said that you want to do a dot product of two k segments. Okay, so k segment is basically like a segment of length k, and then okay, so one quick thing, someone asked in the chat, any specific reason for keeping k up only up to 5 into 10 to the power 7? I guess it was mostly so that I mean, keeping it higher would have meant increasing the time limit to more than 2.5 seconds, like even more. And I think it's enough to distinguish between the slower non-bit set solutions and the faster bit set solutions, I guess. Um, I'm not exactly sure as to why exactly 5 into 10 to the power 7, but okay, so what does this want? What does this problem effectively want? The statement is kind of simple to understand. So you are given an array let's use this tool. This is something I discovered today only. So right, so we are given an array, and let's say I think even k is given here. Okay, so m and k. So m is given here. So m, let's say m is 3 for our purposes. So it's saying that f, so it has this function f. So fi comma j, oops, fi comma j is just, so let's say I is basically this index and j is this index. So it means that we take this section I starting from I and having length m. We take this section starting from j and having length m, and then dot producting these two kind of subarrays. So what does dot product mean? It means multiplying the corresponding parts. You multiply this with this. Right, sorry. Yeah, so you multiply this with, what's happening? This place. You multiply the second position with this position, and then you multiply this position with this position, right? So it's effectively like dot producting two vectors, and then you take the sum. So that is fi comma j. M is a fixed quantity given at the start of the problem. So what we do, we have to compute. We have to compute the sum of all ij, rather sum of all fij, so that rather not so that, like sum of all f of I comma j, where I and j can vary from 0 to n, rather not n minus m plus 1, I guess, because I mean obviously you cannot have n, right, because n plus m will exceed the array bounds. So yeah, it's effectively you want to find some s from I to n minus m plus 1, j from n minus m plus 1 of fij. Basically all values of ij, all combinations of values of ij, you want to find the sum of fij and modulo some large number, right? So what's the most direct way of computing this? If you know, if you want to just calculate fij, you can do a order n computation, right? Not order n, order m computation. So each fij, if you do it very naively, it will take order m computation, right? And you cannot really make this any faster, right? Like given two random ij values, you cannot really calculate fij any faster than order m, most probably. Yeah, because even if you somehow want to try to convert it into vectors and all, not really possible to compute it faster than this. So I cannot really speed up calculating fij, right? Okay, okay, let's just go over what the basic complexity of a knife calculation would be. I can vary over order n values, right? Same for j. So it's effectively order n square into this order m thing. So m can also vary over value till n, right? So it's effectively an n cube calculation if we just do as the problem says. Does it fetch us many points? Not really. It doesn't fetch us anything actually. Interesting. Okay. So now the next part of the problem also has updates. Okay. So as if this wasn't hard enough, it also has updates. What are the updates? You can change the value at a certain index to a given value, right? So updates are of the form pos comma val. You are changing a of pos to val. Okay. So this. So initially, if our array was 1, 2, 3, and you wanted to change the index of 2 to some value 5, then you have 1, 5, 3, right? And after each of these changes, you again have to calculate s. And even the number of queries is quite large, right? 10 to the power 5, 5 into 10 to the power 5. Okay, so how do I kind of approach this problem, right? So so n can vary up till 10 to the 6, q can vary up till 10 to the 6. So it's kind of obvious that firstly the formula can be simplified, and secondly, to facilitate these updates, there must be some data structure involved using like in this problem, right? And you cannot do square root decomposition because again, I think I talked about this last day. 10 to the power 6 is just too high for square root decomposition. So something like a segment tree, you might guess that okay, somewhere there might be a segment tree involved, especially since these are in the form of point updates, right? So maybe somewhere segment trees are involved. So our first question is, how do I simplify this formula? Fij, you are taking sum over all I comma j, right? Okay, so let's try to do something. Okay, I'll actually take the help of the editorial here, to be honest, because the formulas are very well written in the editorial, and drawing using a mouse is like very hard. So uh, I'll just go into the editorial and explain how the things work, right? So see, our effective problem is, remember what Fij was? Let me show you once again. Fij is effectively this summation, right? You are doing if I have fp comma q, then I am just doing p plus I into q plus I for I from 0 to m minus 1. Um, yeah. So we are effective, and then this summation s, you had two summations uh, in front of Fij. We are just replacing Fij with this formula, okay? Right. So effectively, this is the sum. Now, an interesting property of summation is you can reorder stuff when the summations are kind of independent. So you see, I, j, k are all kind of independent variables, right? No one is depending on the other. You are doing a sum over all of them. So it's basically this technique is also sometimes known as double counting, in if you are more familiar with math competitions. So this is kind of like a double counting in the sense that you are anyway computing all like anyway calculating all the specific values. You are just reshuffling the order in which you are calculating, right? So you can basically interchange the summation. So something like here, ai plus k, right? For k is equal to 0. So you can take this ai plus k common outside. Okay. So the first thing that he is doing is, the first thing that we do, both of these terms have the term k, right? ai plus k and aj plus k. So instead of keeping the k loop fully inside, what we do is we shift the k loop fully outside, right? So instead of doing summation I from 0 to n minus m, summation j from 0 to n minus m, summation k to 0 from m to m minus 1, what we do is we first do summation k to m minus 1, and inside that we include for all I from 0 to n minus m, for all j to 0 to n minus m, and inside that ai plus k into aj plus k. Does this make sense? Like how I am like reshuffling the summation signs? I'll just draw it just to make it clear once again. Okay, so first we had this summation was over the variable I, right? Then we had a summation over the variable j, and then we had a summation over the variable k, right? And here we had that aj into ak part, right? So I'm just denoting it as a into b, just for notation's sake. What we can do is, since that a is basically ai plus k and b is basically ai j plus k, so since they don't depend on each other, we can very well just change these signs. We can make this k and we can make this j, make this I. Okay, so we can shuffle this summation signs around as we want, because it's not like the inner summation actually depends on the value of the outer variables, right? The variables are independent of each other. So that's why we can do this thing. Now, how does this help us? So see, here the editorialist effectively did the same thing. So how does this help us? This k part is actually now at the starting, see, and now inside the double summation that we still have from I to 0 to n minus m and j to 0 to n minus m, the k, like the ai plus k and aj plus k part is anyway constant. And we can also, since the first summation is I here, we can also pull out that ai plus k term, right? Because the ai plus k term is always constant whatever the value of j is. So we pull it out, correct? And then we just have a summation j from 0 to n minus m aj plus k, right? I hope it's clear why we can pull out that I plus k term outside of that summation. Okay, so here we denote the sum of the subarray LR by ALR. So he is effectively doing that this summation j plus k for all j 0 to n minus m. This is effectively what you are starting at k and like k plus 0, and then you are going up to k plus n minus m, right? You are taking the sum over all these values. So that is effectively the subarray sum of as like of the array a from in a range, right? So we are effectively doing a k comma k plus n minus m. Now this term that we got a k comma k plus n minus m, this is a subarray sum. The notation with the subscript, that is a single element. This part is again not varying according to I, right? There is no term of I. There is only a term of k, and there is n minus m. N minus m is anyway a constant. So we can again take this out as in the next step, as it's shown. And then we again have the I from 0 to n minus m, a of I plus k. So this is the same thing as the previous thing that we substituted, right? We can just substitute it by a comma a into k comma k plus n minus m. It's like just how we substituted in this step, correct? And then it's effectively we are having the same thing here, so it's just a whole square value, right? So see how we reduced a triple summation to just a sum of squares, right? So when you see the problem, so it might seem a bit complicated that, oh, how do I get till this point? So when you see the problem, right, when you see that, okay, I cannot really simplify Fij and still I have to compute the summation, that means you cannot really iterate over Ij and calculate the value of Fij. You instead have to somehow manipulate the summations so that it's a bit faster to calculate stuff, right? And obviously you cannot have 3 loops of order n time, so you have to somehow eliminate the sum of the loops, right? And then that is how you get the intuition that, okay, maybe if I write it down and if I like change the summations, and it's kind of a common trick that we use. If we have some double summations, we can usually swap the summation signs to simplify it. So that is kind of the intuition behind why we write it as a triple summation and why we think that, okay, maybe it can be simplified, and we finally actually get the simplification, right? So now this k value, so now we only have to iterate over this k value, right? And for each k, we have a particular value, right? A k comma k plus n minus m is a particular value. I'm not considering any updates till now. So effectively what we have is we have some squares, like rather we have some numbers a1, a2, a3, a4, a5, and then we have to calculate sum of squares of them for the whole range, right? So so if there was no queries, right, in the, let's say in the first subtask, there are no queries, right? Or rather there is only a single query. Yeah, so a single query effectively means you just replace the position and then calculate the sum. So effectively no queries. So if you have such a situation, you can just get this ak comma k plus n minus m values, right? This is just a subarray sum, and you just square it, add it. That's just a linear thing, right? Subarray sum can be easily done using prefix sums. Yeah. So till this part, how we are reducing it to just calculating sum of squares of certain values. Is there any doubts, any confusion, why we are doing it, or how do I get the intuition to do it in this fashion? Is there any doubts up till now? You can tell in the chat maybe. Uh, okay. Okay, so someone asked how we can use square root decomposition in this. Um, See, square root decomposition is not possible in this problem primarily due to the fact that the constraints are so high, right? 10 to the power 6 is too high for us. Anyway, so now what do we have? So now we have some updates, right? How do we handle the updates? When we update a certain index, we are updating the values of, so let's call these a k plus n minus m as bk. Okay, so we use this shorthand. Bk is effectively a k comma matlab somewhere is sum of k to k plus n minus m. Okay, and we just have to find bk square. So when I update a certain position, a lot of these bk's can get updated, right? Because let's say so let me my previous array here. It's not coming. That side. Yeah. Right, and then we have something like, so let's say n, like the length of the subarray is fixed, right? I go from k to k plus n minus m. So the length of the subarray is just n minus m. Let's consider here that n minus m is some value, let's say 4. So what is bk? Bk is the sum of this region. So b0 is the sum of this region, b1 is the sum of this region, b2 is the sum of this region, and so on, right? So if we update the value at this particular position, b0 gets updated, b1 gets updated, b2 gets updated. So a lot of the bi's get updated, right? Now what do we observe? That the bi's that do get updated, they form a contiguous region, right? So here let's say b0, b1, b2 gets updated. Anything onwards to b3, from b3 does not get updated. So what is kind of how, what do we reduce it to then? Now we are given two kind of things. We have to build a data structure, right? So one thing is obvious, that this needs a data structure. We cannot do this naively. So what does our data structure have to offer? You can do a range addition, right? You can do a range addition to a, or rather a range, not uh, yeah, a range addition. And then another thing is, for like, you also have to calculate sum of squares of all the indexes. Okay, so these are kind of the two queries that your segment tree needs to support. So for some of the squares, it's always advisable to store only the sum also. So let's say for a node, so let's say we have a segment tree like this. um, so let's say this is some like our segment tree. So what we stored is, for each node, let's say for this node, this represents some portion of the array, right? Let's say it represents this portion. Okay, so drawing is not to scale. Yeah, so let's say it represents that portion. What does this node contain? This node contains, firstly, the sum of all the elements in the region that the node represents, and also the sum of squares of all the elements. So if the elements were b1, b2, b3, rather, yeah, b1, b2, b3, b4, we can it firstly it contains b1 plus b2 plus b3 plus b4. It also contains b1 square plus b2 square plus b3 square plus b4 square. Okay, so it contains both of those two values. what is our answer when we query the segment tree for sum of the squares? It's just the value of the root, right? Like one of the values of the root is a1 square plus a2 square plus a, like, sorry, b1 square plus b2 square plus b3 square up till bn square. So root contains sum of squares of all the numbers. Also, it contains the sum of all the numbers, but we are more concerned with the sum of squares, right? And then the when we update, so update is a bit tricky. See, firstly, it's clear that we need to use lazy propagation, right? Because we have range updates. We are adding some value to the entire range. Now, if we just had to maintain sum, that is just our usual old segment tree lazy propagation, right? When you come, like when you rebuild those two nodes, you take the sum from left child, sum from right child, add them up. And if you are ending at a node, and like during a lazy update, when you are ending at a node, you basically push down the lazy tags, right? And then you have to somehow calculate, like lazy updates end at intermediate nodes, right? So you have to somehow calculate the values for the intermediate node. So for some, it's just if you add d to the entire range, then you just add d into r minus l plus 1, right? Because a node has r minus l plus 1 elements, let's say. So if I add d to all the elements, that means our total sum for that node is increased by d into r minus l plus 1. This is the plain old segmentary lazy propagation. The tricky part is we also have to maintain sum of squares. Now segment trees, there are two important things that we need to consider while doing lazy propagation. First, if we know the value of the left child and the right child, can we combine it together in our node? This is easy to do, right? Because even for sum, you just add the two values. For sum of squares, you again just add the two values of left child and right child, and you are done. The tricky part is how do you do the propagation part, right? So when you end, like when you are doing a lazy propagation and you come to this node and you end here, right? Let's say this entire node falls under the range where what I wanted to update. You are ending your DFS, or rather not a DFS, your traversal at that point, right? You are not going anything below, because if you went below, you have to visit both the child. You don't do lazy propagation like that, so you stop there. How do you update the answer for that node? For some, it's easy. For sum of squares, it's also doable. How? See, how do we write sum of squares? So let's say all the elements got increased by d. So we initially had a square. Okay, I'll use something else because writing is painful. Yeah. So we initially had a square plus b square plus c square, right? So we call this sum. So we call this sum prev, or rather sum p1. Okay, so sum p1 means the value before this update, and this is just sum of squares. And sum p0, let's denote it as just a plus b plus c. Okay, so 0 effectively means sum of the elements, and sum 1 effectively means sum of squares of the elements. P is just to denote that these were the values before my update. After update, what do we have? So sum 0 now is just a plus d plus b plus d plus c plus d, right? And sum 1 is a plus d whole square plus b plus d whole square plus c plus d whole square, right? Like this, right? Okay, let me change the font a bit. 24. Yeah. So my job is, given sum p0, sum p1, and d, how do I calculate sum 0 and sum 1, right? Sum 0 is very easy to calculate from sum p0, just the normal sum calculation. How do I calculate sum 1? So sum 1, we try to simplify it like this. So we have our a square plus b square plus c square terms, right? We just expand the formula. Plus, we have our d square term 3 times, correct? We have our d square terms into 3. Plus, what do we have? we have 2AD plus we have 2BD plus we have 2CD, right? So how do I, what is this effectively? This is basically sum P1 plus, so let's say our range had 3 elements, that is why we do 3 into D square plus 2 into D into A plus B plus C, right? Sum P0. This is all we are doing, right? This is how we calculate sum 1 after the update during the lazy propagation step. Because in lazy propagation, we don't know the values of the left and right children individually. We have to update this value with the value of the node directly. So sum P0, you know from the previous, like sum P0 is the value currently stored in that node. Sum P1 is the value stored in that node. D is kind of your lazy propagation thing, right? The lazy value that you are propagating effectively. And how do you recalculate the values of the nodes? Sum 0 is effectively just sum P0 plus 3 into D. So 3 is because we have 3 elements in our range we are considering, just as an example. And for sum 1, it's just you do sum P1, right? Plus 3 into D square plus 2 into D into sum P0. This is just how you update the node of the segment tree when you are ending your lazy propagation at that step, right? When you're pushing the values, that is the only part that you need to take care of. We did this for, I showed the example for 3 variables. You can have any number of variables. Only the what will matter, this 3 will become, let's say, 4 or 5 or 45, depending on the number of variables, right? Like rather not number of variables, the range that node represents in our original array. So this is how you maintain that segment tree when you have updates. And for query, you just return the sum 1 value of the root node. Yep. So that was the entire thing. Any doubts, any queries? Do you want me to like go over the segment tree part again? Maybe write in the chat. Like after this, I'll just quickly go over tree query. Maybe like yesterday I had said that I'll discuss the segment tree approach for like what to do in the segment tree for tree query. So if you don't have any doubts in this problem or in tree query, you can like that's what I'll be doing next. So okay, so one question is, why are we updating every value when only values at a position is to be updated? So see, in the original array, we were updating a position, right? But what are we building the segment tree on? We are building the segment tree on B values, right? The B array that we had generated here, let's say in the editorial also, if you want to see, we have this bk is equal to ak comma k plus n minus m, right? So we want to calculate the sum of squares of bk. Now that is the B array is what I'm building my segment tree upon. When I do a point update on my original array, a range of values in my bk can be updated, right? Because bk is effectively denotes a particular range of that initial array, right? So b0 is like this, b1 is like this, b2, b3. When I do a particular point update, a lot of b values can get changed, right? Because a lot of b values might have that position inside their range. That is why there will be like many different b values that needs to be changed. What is the nice property of like about which b values get changed? All the b values that gets changed have contiguous indexes. That is why we are able to use a segment tree here. Does that make sense? We are building the segment tree on the B array, not the A array. Hence, each update to the A array is actually a range of updates in the B array. I'll just give a very brief review of jumping fever. See, I hope everyone has read the problem. There is a very similar problem on code forces, I think. I'll link the problem. I'll link this problem. So I'll post the problem here as well. So this is a simplification of that problem, kind of, in some sense, right? And okay, wait, I posted this privately. Meeting, yep. And so the basic idea kind of is we have to maximize this f values over all paths, right? So whenever I see all paths, I kind of tend to think towards centroid decomposition, because problems are usually of that sort. When you try to compute some value over all possible paths, usually centroid decomposition is the way to go. Moreover, we can, so how it's described here is like you do suffix, you add all the suffix sums together. So you can kind of think of it like you are doing ai into I, rather like a1 into 1, a2 into 2, a3 into 3 in the total s that you get, rather fuv. So it kind of, because like if you break the path at one point, or if you want to combine two paths, it's like uh, if the first had length k and the second k1 and the second path had length k2, then you are effectively, like in the second path you are computing it as b1 into 1, b2 into 2, b2 into 3, b3 into 3, something like that, right? If you join the two paths, it will effectively become b1 into 1 plus k, rather k1, b2 into 2 plus k1, b3 into 3 plus k1. So k into sum of bi, that gets effectively added. So that is in the form of a convex hull. You can think of them as lines, and maybe you can do it as a convex hull trick optimization, right? And then there are more values to compute there here, like you have to compute two dps, in the sense that what is the best path I can go get from some node u to any node in its subtree, and similarly what is the best path from sub node in my subtree to my current node. These two dp values can be calculated using um, something like DSU entry trick. It's basically like small to large trick, but it's called DSU entry. So it's a bit complicated, and we will do a separate video completely on this. So yeah. Okay, so for triangle query, okay, so lastly, just the segment tree for triangle query. What was it again? Oh, okay. So yeah, so what our segment tree would have looked like in triangle query, I'll just go over it quickly. So we have our frequency array, right? We have this frequency array. Okay, very poor diagrams, but why not? So this is, let's say, 0, this is 1, this is 2, this is 3, this is 4. So these are the indexes, kind of, right? 6, 7. So let's call this the array f. So in that problem, f of 3 would have meant how many values, rather remember that we had talked about a z component, rather a z property of a point. F of 3 effectively means in whatever values I have seen till now, how many of them have z equal to 3, right? So let's say 2 of them had z equal to 3, then we would have a value of 2 here, and the rest of the values are 0. Let's say one of them had a z equal to 5, then we have a 1 here. Let's say three of them have z equal to 3, right? So when I do an update, so we had built a segment tree on this f array. When I did an update, when I got a z value of, let's say, 2, I basically came into the segment tree and I updated the position corresponding to the value 2, right? And we did a plus 1 here, right? Another time, if we got a value of 3, we did a plus 1 here, and this value would have become 3. Sorry for the bad drawing, but yeah. So this is how we had updated the segment tree. And when we want to query how many values are greater than a, we just do, let's say, how many values are greater than 3. We effectively want to count the number of occurrences, or rather count the sum of this region, right? So starting from a till the end of the frequency array. So that is what we wanted to do yesterday. Uh, if anyone had any doubts in what segment tree or what data structure we were building, it was just a segment tree on the frequency array, right? So yeah, so I guess there are no doubts, at least in the two problems that we discussed today. And if anyone had any doubts in the segment 3 portion, this is it. Yeah. So is there any more doubts, any more questions, anything you wanted to ask? Okay, so I guess then that's it for today.